Hi, and welcome to Mr. DeCrane's video on exponent and log functions. In this video, I'm going to show you how you can graph a logarithmic function based on your understanding of the corresponding exponential function. So you're going to need a piece of graph paper to start, and I want you to make a table of values and graph y equals 2 to the x. Make a good table with negative and positive values for x, and make a nice graph, pretty accurate one. You're going to need graph paper for that. I'm going to pause the video here for a minute and then get that table and graph going, and I'll join back with you in just a minute. So this is what the table looks like. You see I've got some positive values for x and some negative values for x in my table. And since it's 2 to the x, the y values are just doubling: 1, 2, 4, 8, 16. As we go negative, they get cut in half: 1/2, 1/4, 1/8. And if I start to graph these, the graph, I have the wrong color there. Let me get a better color. So it corresponds 1, 2, 2, 4, 3, 8, 4, 16 is off the grid, so I'm not going to graph that one. These guys, remember, the y values here get smaller and smaller, closer and closer to 0. So we have that asymptote along in here, and the graph looks like this. So let's identify some key features here. The domain is all real numbers. The range has got to be y is bigger than 0. There's an asymptote at y equals 0, and that's pretty much the key features of this. We've got the y-intercept right there. We've got another point where x equals 1 to help keep us in line, and that's what the graph looks like. Now remember, go back to what we learned about logarithms before, and we can translate this y equals 2 to the x into a logarithmic expression by saying log base 2, remember the base stays the same, of y equals x. The exponent becomes the result of the logarithm. And if we do a quick switcheroo, we can write this as log base 2 of x equals y. Remember, that's how we find the inverse function. We switch the x and the y. And if we make a table of values for this one, remember when we do an inverse, that just switches the x and y values. So 1/8 comma -3 becomes a point on this graph. And since -2, 1/4 is a point on the original, 1/4 comma -2, 1/2 comma -1, 1, 0, 2, 1, 4, 2, 8, 3, and 16, 4. And if I start to plot these, let's see, 1/8 comma -3 is really close to the y-axis and way down there. 1/4 comma -2, 1/2 comma -1, 1, 0, 2, 1, 4, 2, 8, 3, and again 16, 4 is off the grid, so I'm not going to graph that, but this gives us a pretty good idea about what the graph looks like. And there, just like that. Again, pause the video here and make sure you've got that nice graph and a good table of values for this new function log base 2 of x equals y. I'll wait. Okay, so you've got the graph. Let's talk about the features here. Going back to what we learned about inverses, remember, inverse functions are reflected across the line y equals x from their parent function, and if we treat this dotted line along y equals x as a mirror, you can see that the two graphs kind of match up pretty nicely. Also, notice that the domain here is x is bigger than 0, because I'm all on the positive side of the x-axis. And the range is now all real numbers. Hey, our x's and y's switched on inverses, like they always do. Instead of domain being all real numbers, range is all real numbers. Instead of the range being y is bigger than 0, the domain is x is bigger than 0. The x and the y switched. Also, note that the asymptote is now x equals 0. It is a vertical line, asymptote right along the y-axis. And so that's a basic logarithm function. And if we know the corresponding exponential function, we can graph the log function pretty nicely. Let's take a look at another example. This one, we're going to start with the log function. What we want to do is identify the key features of this one and then graph it as well. So what I'm going to do is I'm going to switch it around to an exponential. Remember, the base of the logarithm becomes the base of the exponential. The result of the logarithm becomes the exponent. So I get 2 to the y equals x plus 6, or 2 to the y minus 6 equals x. And if I switch it around, I'm going to get 2 to the x minus 6 equals y. That's the inverse. And if I can identify the key features on this one, oh, I'm sorry, I wrote 2. I meant 3 for the base there. My bad, sorry. Thank you for catching that. 3 to the y, 3 to the y. So this is then 3 to the x. The base of the logarithm becomes the base of the exponential. Sorry about that. So 3 to the x minus 6 equals y is the inverse function. Notice that's an exponential function. I know a couple of points on here. I know that the asymptote is at y equals negative 6. I know that y-intercept is 0, let's see if I plug in 0 for x, I'm going to get 3 to the 0, which is 1. Minus 6 is negative 5, 0, negative 5. I know another point on the graph is going to be 1, let's see, 3 to the first is 3, minus 6 is negative 3. And so I can graph that one pretty nicely. Let's see, y equals negative 6, 1, 2, 3, 4, 5, 6 down. So that's my asymptote. 1, 2, 3, 4, 5. There's 0, negative 5. 1, negative 3 is there. And I can make a few other points. 2, 3 squared is 9, minus 6 is 3, so 2, 3. It's way up there already. Remember, when the bigger that base gets, the steeper this gets really quickly. And so the graph looks something like that. And if I know that exponential, I can figure out the logarithm graph, because all I have to do is switch the x and the y. So for this one, I should do one more thing. Let's identify the domain and range here. The domain on that exponential graph is all real numbers, and the range is y is bigger than negative 6. So for my logarithm graph, my domain is going to be x is bigger than negative 6, because I got to switch x and y, and my range is going to be all real numbers. My asymptote is at x equals negative 6. I have a point at negative 5, 0. Ooh, I know the x-intercept now, not necessarily the y-intercept. And let's see, I know that negative 3, 1 is on the graph. So I'm going to plot those things, 1, 2, 3, 4, 5, negative 6 in the x direction. So there's my asymptote for the log graph. Negative 5, 0, 1, 2, 3, 4, 5, negative 3, 1. I also had 2, 3, so that becomes 3, 2. It's over here, and I can kind of see where this graph is going to go, just like that. And so that's my logarithm graph. This equation that we started with has this graph. A couple of details to note. It's always increasing. We can talk about some limit information. The limit as x, I'm sorry, we're not using limit notation yet. That's the other class. We can say the end behavior here is x goes to infinity, y goes to infinity, but slowly. Notice that's pretty flat. It doesn't completely flatten out, though. It keeps growing. As x goes to negative infinity, y is undefined, because we can't get past that asymptote. The domain doesn't go to negative infinity. It only stops at negative 6. We can say as x approaches negative 6 from the right, y goes to negative infinity, and that's how we describe that graph. I hope you enjoyed this. Watch it again if you need to, and hopefully that gives you a leg up on how logarithm graphs work. Thanks. Bye-bye.